Let's complete our survey of trigonometric graphs by examining the graph of cotangent. Recall that on the unit circle, the definition of cotangent of an angle alpha is equal to the ratio of the x-coordinate to the y-coordinate. So we can see that when the input, now in order to not be confused about notation here, let's call that angle alpha. When the angle alpha equals pi over 2, cotangent of pi over 2 is x divided by y, or 0. This point will anchor our graph on the x-axis. Now, as our angle alpha approaches 0 from the right, this little positive in the exponent position is a directional indicator. That means we're taking our angle from pi over 2 to 0 radians from above. So as our angle decreases from pi over 2 to 0, the value of cotangent changes as well. Now, the value of cotangent at pi over 2 is 0, as we've observed. At pi over 4, the value is 1. So notice the value of cotangent is increasing from 0 to 1. As the angle changes from pi over 4 to 0 radians, then the value of cotangent goes from 0 to, now look what happens here, x divided by y, 1 divided by 0 is undefined. However, as we mentioned in the previous video, we could make the observation that as the denominator decreases and the numerator approaches 1, the value of cotangent approaches infinity. Making a similar observation on the other side, we could say that as the angle alpha goes from pi over 2 to pi, then the value of, correct my typo, sorry about that. The value of cotangent of the angle is also going to change. Now, notice as the angle rotates from pi over 2 to 3 pi over 4, the value of cotangent goes from 0 to -1. Then, as the angle continues rotating around to pi radians, then the value of cotangent approaches this undefined value, -1 over 0. As the denominator approaches 0 and the numerator approaches -1, we're going to see the value of cotangent plunging down to -infinity. Let's translate this information to a graph, and we'll see how our analysis helps us to understand the pattern of cotangent in the coordinate plane. To begin graphing the cotangent function, let's first observe that cotangent of 0 is undefined and cotangent of pi is undefined. This creates a vertical asymptote on the graph at x equals 0 and x equals pi. We can then evaluate cotangent at other angles to generate some points to plot. At pi over 4, cotangent has a value of 1. At pi over 2, cotangent has a value of 0. And at 3 pi over 4, cotangent has a value of -1. So we have 3 key points to generate the shape of cotangent. We have the point pi over 4, 1. It's going to cross the x-axis at pi over 2, 0. And it's also going to contain the point 3 pi over 4, -1. Connecting the dots reveals the basic shape of cotangent. Remember, as the angle goes from pi over 2 to 0, the graph of cotangent approaches infinity. And as the angle goes from pi over 2 to pi, the graph of cotangent plunges down into -infinity. Though the nature of cotangent is very similar to the nature of tangent, observe that cotangent is a decreasing function. Tangent was increasing, but cotangent is decreasing. Also notice that cotangent's first fundamental cycle has been shifted horizontally from tangent's fundamental cycle. But we could make the observation that, like tangent, cotangent has a period of pi. Just as one fundamental cycle occurs in a distance of pi, we can repeat this shape every pi units on the x-axis. So we could predict the next vertical asymptote would be pi units later at 2 pi, or over here on the left side, pi units before 0, we would have a vertical asymptote at -2 pi, and also at negative pi. The basic shape of cotangent then repeats periodically across the entire x-axis. So where one fundamental cycle lies between 0 and pi, we can see the complete graph of cotangent repeats this process over and over again. This means that cotangent has an infinite number of asymptotes, but it's easy to detect the pattern. An asymptote occurs at every integer multiple of pi. So the equation of all of the asymptotes on cotangent could be expressed as x equals k pi, where k is an integer. Similarly, the domain is going to be the set of all x such that x does not equal k pi, where k is an integer, as those values lead undefined results for cotangent. And like tangent, the range of cotangent is from negative infinity to infinity. Just as all of the transformations applied to tangent, we're going to see similar transformations applied to cotangent. So let's practice manipulating the graph of our basic parent function to graph transformations. In example 5, we want to graph 2 cycles of y equals cotangent of x over 2. The first thing that we want to observe here is that this particular cotangent graph has a change in the period. We could rewrite that argument as 1/2 times x. Because the argument has been multiplied by a constant, this results in a change of the period. To figure out what the period of this new function is, we're going to take the period of the original cotangent function, which is not 2 pi, but pi, and divide by this coefficient. Then we can cure this complex fraction by multiplying by the reciprocal of the denominator, and we can see that the period of this new transformed function is 2 pi. Remembering that the original cotangent function achieves one fundamental cycle in the interval from 0 to pi, we could say this cotangent function will achieve one fundamental cycle when the argument ranges between 0 and pi. Solving for x, we can see that the fundamental cycle for our transformed function is going to be from 0 to 2 pi. At the beginning of this fundamental cycle, we have a vertical asymptote that's located at x equals 0, and at the end of this fundamental cycle, we have a vertical asymptote at x equals 2 pi. Just as cotangent, the original function, crossed the x-axis halfway between its 2 first asymptotes, our new transformed function is also going to cross the x-axis at the midpoint between its first 2 asymptotes. Then, halfway between the midpoint and the first asymptote, the value of tangent is 1, and halfway between that x-intercept and the last asymptote, the value of cotangent is -1. As cotangent decreases, it's going to snake its way right through the x-axis. Observe that the change in this period causes a horizontal expansion of the graph of cotangent. Now, in order to graph 2 fundamental cycles of this transformed cotangent function, we can repeat this exact same graph on the other side of the y-axis. Notice that 2 pi units before that first asymptote, we would have another asymptote at x equals -2 pi. At the midpoint between those 2 asymptotes, cotangent crosses the x-axis, and then we could plot the corresponding locations of cotangent, having a value of 1 and -1, and connecting the dots to repeat that nature. Now we can see 2 cycles of our cotangent function. Because the asymptotes occur every 2 pi units apart, then we could write the equation for every possible asymptote of cotangents, recognizing that it is an even multiple of pi. So if k is an integer, then 2k is an even integer. So whatever value we choose for k, 2k pi will generate the location of an asymptote. And as we've learned, the domain is everywhere except where these asymptotes occur. So we're going to exclude those asymptotes from the domain of cotangent. And as usual, the range of cotangent is from -infinity to infinity. Now let's go ahead and practice a transformed function that experiences a horizontal shift. In example 6, we want to graph 2 cycles of y equals cotangent of x minus pi over 4. So notice, because we're subtracting pi over 4 from the argument, that this graph is going to shift pi over 4 units to the right. So we're looking at the original cotangent function shifted pi over 4 units to the right. Now, if we recall, the original parent function had its first asymptote at 0 and its second asymptote at pi, then we can simply shift each of those vertical asymptotes right by pi over 4 units to obtain the first 2 asymptotes for our transformed function. So notice these would occur at x equals pi over 4 and x equals 5 pi over 4. And where the original cotangent function crossed the x-axis at pi over 2, we can shift that point pi over 4 units to the right and observe that this new cotangent function is going to cross the x-axis at 3 pi over 4. Filling in the general pattern of the key points, we have a transformed function of cotangent. Now, to graph that one, I was simply imagining the parent function and shifting it pi over 4 units to the right. Another way to determine this first interval for the fundamental cycle is to make the observation that for the argument to range between 0 and pi, cotangent will achieve one fundamental cycle. So I'm taking the argument and I'm trapping it in between 0 and pi. If we add pi over 4 across this entire function, 1 pi plus 1/4 pi would give us 1 1/4 pi, or 5 pi over 4. So you can see with an inequality analysis, you can also determine that interval for your first fundamental cycle. Now, because there was no coefficient on the x here, this function does have a period of pi. So if I find the distance between 5 pi over 4 and pi over 4, that is, if we subtract 5 pi over 4 minus pi over 4, we'd end up with 4 pi over 4, or pi. So the period of this graph of cotangent is pi. Now, don't let these asymptotes intimidate you. A very easy way to generate the formula for all of the asymptotes of the graph is to start at the smallest positive asymptote, which we can see is at pi over 4, and then add an integer multiple of the period. So if we add k pi units, we're going to land at another asymptote. As always, we need to specify that k is an integer. With this in mind, we know that the next asymptote would occur at pi over 4 units to the right of 2 pi, or 2 pi plus pi over 4, that would give us 9 pi over 4. Then we could easily see another snapshot of that fundamental phase of cotangent there in the middle. You can graph 2 cycles by either putting another copy on either the right or the left. It doesn't matter. Now, the domain of this graph is going to be everywhere except where those asymptotes occur. So make sure you get not equals there in your domain. X is not equal to pi over 4 plus k pi. Do specify that k is an element of the integers. And the range, no surprise here, -infinity to infinity. So at this point in Chapter 2, we have looked at the fundamental cycle for sine, cosine, secant, cosecant, tangent, and cotangent. We have also explored how to apply all of the ordinary algebraic transformations to the trig functions. So we have a pretty comprehensive view of the graphs of all 6 trig functions.